So we discussed about the finite element time domain method. So since it is a time domain method, you may also require PML layers. No, the PML layers we have already discussed in detail when we study FTDD time domain. We have discussed split field PML, we have discussed stress coordinate based PML, and for the FETD, I think it has been reported that the uniaxial PML actually gives better performance than the other cases, split field and the stress coordinate based PML. So if you want to implement PML for the FETD, then you should actually go for the uniaxial PML. Okay, so today morning, Siddharth was sent an email about this doubts. He has 5 doubts he has. First question is, while you are discretizing any finite element, how you decide which section to divide into triangular section or rectangular section or any other kind of section? Like in example, you have divided the finite element into triangular section. So can I divide it in rectangular section and I do this? Will it then give the same? See, basically the choice of the subsection is purely yours and it's your convenience, no? And it is dependent on the shape of the you are doing discretization, or let's say this structure here. Let's say had it been some rectangular shape, then obviously it would be easier for you to discretize using the rectangular shape function, and usually we use triangular shape function because triangular shape function can actually model the curves also. So depend on what kind of discretization you want to do, and the only thing is that once you discretize it for triangular element or let's say rectangular element, then you have to use the corresponding shape or interpolation functions, and if it can fit in all the solution space, then it is always better. If you leave out something here, then it is going to give you less accurate results. So if triangular is fitting well in such kind of structures, then you should actually use triangular. And if any kind of structure which is very good for you to model using the discretization using the rectangular shape, you can always go ahead. So that is your personal choice, and you should have a judicious choice so that you should not leave out any of the solution space here. So that's why people are using this triangular shapes elements of different size here. So if you want to go for higher accurate result, then you should not leave out any solution space here. Second question is, except triangular and rectangular section elements, it should be elements, what other geometrical figures you can use for discretization? See, basically you can, depending on what you're modeling. For example, you want to do 3D shapes, then you cannot use, let's say you want to do volumetric discretization, you cannot use triangular, rectangular shape. There people use pyramidal shapes also. So any kind of element we should be able to discretize properly the shape you're choosing, you have to use those kind of shapes. For example, pyramidal is one, just like triangular can model any kind of arbitrary. And question number 3, in page 58, 59, two methods are discussed. One is band matrix and iteration based matrix. This method gives more accurate result because in the example discussed, there is a slight variation in the solution. So basically there is no hard and fast rule for that. If you use iteration based method, you have to have a judicious choice of the initial solution, starting initial solution. If you have taken it very judiciously, you should be able to reach to the final solution as soon as possible with less number of iterations. And if you go for higher and higher number of iterations, you will get a more accurate result. So if you get a convergent result, then you cannot, you do not go further, you can stop there. So in the example, maybe we are not getting the convergent result. We need to go for more iterations to get similar kind of result what we are getting in the band matrix method. But band matrix method, actually you have to do sorting of the free nodes and prescribed nodes. That's the additional work you have to do for the band matrix method. And in page 76, to satisfy Euler's equation, you need to find functional. How to find functional assuming phi x is given. That's a purely mathematical problem. We are not considering this kind of problem here. Phi x is what we are trying to find in the FEM, and phi x was actually there in the PDE we are solving. So in our case, we have used in the variational method. See, there are two methods here. One is direct method, one is indirect method. In the direct method, we can use Galerkin's method of weighted residuals and directly find the PDE along with the boundary conditions and find the phi, which is the unknown function. Or you can have indirect method in which you actually find an equivalent functional and you try to minimize that equivalent functional and you get the same solution. So it's easier for us to see. That's one technique, variational method. One is the Galerkin's method of weighted residual. So depending on what method you follow, you different procedure there. So this is basically for the variational method where you use calculation of variation of finding an equivalent problem and you actually find the calculation variation. And here we actually do not find a functional for f for the phi x. See, phi x is given. So phi x is what we are finding here in FEM. Phi x is not given and we are not considering those kind of problem. But let's say phi x is given, which functional will give me maxima, minima. That's a purely mathematical problem. We are not looking into such kind of problems in the finite element method. And in phase 71, why do we have to find extremum value of I phi? So function. Okay, so as I have told you in the previous question also, FEM has two approaches. One is direct approach, another is the indirect approach. In the direct approach, you use to find the PDE boundary value problem by applying Galerkin's weighted residual method directly. In another method, we actually find an equivalent problem where minimizing. So this is actually, we have proved it also. We have seen that when I minimize the PDE, when I minimize the functional, then I am getting the exact PDE. And when I actually find there are two ways. From the PDE you find the functional, from the functional you find the PDE. We have done both ways. So it's equivalent problem. We have already solved it. We have proved it also. In the process we do that when we minimize it. So physically, if you want to look at it, so probably you are asking physical meaning of that. Let's say functional is energy. You minimize the energy, you have a stable solution. So stable solution is what we are looking for. Or let's say you want to find any kind of arbitrary physical problem, and when you do this functional, you find extremum, that is basically minima or maxima. In that case, you get the equivalent point. So that's why we are doing this physical meaning. Okay, so let's go to what we are going to discuss today. This is actually very, like I said, this is employing such kind of elements, vector as element. So basically, we have considered finding potentials, which is a scalar quantity. For there, we use all the interpolation function or the shape function as scalar quantity. But in many electrodynamic problems, we actually want to find the fields. Fields, maybe electric field, magnetic field. So fields are all vectors. So it is more logical to use, vector shape or interpolation functions. So that's the idea behind that. So most of the, even let's say you want to solve a wave equation is for vector wave equation. So why don't we directly use the vector interpolation or shape functions and solve it? That's more, that will actually, we'll see that actually satisfy the boundary conditions. This kind of vectors here will also satisfy boundary conditions. So basically, let's look at this diagram. It will be more clearer. Let's say you have a rectangular H element. So we want to find out the fill of this rectangular H element. You can actually find it as summation I going from 1 to 4 NIE EIE. So see, what is this NIs? NIs are the interpolation functions or shape functions which are vector. Now I put a vector sign here. So I'm actually approximating the fills inside this rectangular element, and it can be linear approximation of this basis function, which are actually vectors. So what are these basis functions? So let's say if you have a rectangular S element, we consider that in the scalar case also, we have considered triangular element, we have considered tetrahedron, all this Like that, let us consider a rectangular S element and try to find out the fields inside this rectangular S element. So how many edges it has? It has S1. This is, we call this as S1. This is S2. What is the location of the center of this rectangular element is XC and YC. Center, no? C for center. So XC and YC. So coordinates are known, edges are known, what are the lengths, Lx and Ly are known. Let us try to find out what are the vector interpolation or step functions for this rectangular S element. So the vector basis function or interpolation functions for this S element is defined something like this. 1 by Ly yc minus y plus Ly by 2 x hat. So this is the first vector basis function. Second basis function, n2 is 1 by Ly y minus yc plus Ly by 2 x directed. And what is n3? N3 is 1 by Lx, xc minus x, Lx by 2 y hat. And 4 is 1 by Lx, c plus Lx by 2 y hat. Okay, so let us look closely what is this vector basis function. So that's what we're going to do. First thing is that this is the n1. Look at n1. N1 is 0 on the S2. So if you consider N1 is for the S1. So N1 is for the S1. So if you look at this S2, what is the location of Y for the S2? It's YC plus Ly by 2. If you put Y is equal to YC plus Ly by 2 in this expression, this one becomes 0. So N1 is 0 on the S2. So on the edges 3 and 4, what is the value of N1? On edges 3 and 4, you can see that N1 is increasing linearly from top to bottom. So from here to here, it's increasing linearly. So top to bottom, that's what. Then look at this expression. This value of this N1 is going to keep on increasing till here, Along the edges 3 and 4, N1 is increasing linearly. Along the edges 2, N1 is 0. And you can also see that N1 is directed along the x-axis. So this is y-axis, this is x-axis. So along the edges 3 and 4, N1 is normal to the edges 3 and 4. N1 is perpendicular to the, because this is vector is x hat here. So x hat will be directed along this direction. Along edges 3 and 4, these are perpendicular or normal to the edges 3 and 4, this N1. So this basis function actually provide a mixed order approximation of the field. So let us try to summarize. On the edges, the approximation is constant tangentially. Along this S1, what is the variation of this field? Y is constant. Y is constant along these edges. So Y is what? YC minus Ly by 2. So YC and YC cancel out. Then the Ly by 2, it becomes Ly. So it becomes 1. N1 becomes summary means on the edges, along the SY, H1, the approximation is constant tangentially. So it is actually having a constant value and it's tangential along the x-axis. And along the edges 3 and 4, what is that? It is linear normally. It is linearly increasing and direction is along the normal direction. Constant tangential means it is having a constant value and direction is along the x-axis. And linear normally means along the S3 and 4, it is linearly increasing from top to bottom and it is actually normal to the S3 and 4. So this is what? This is a short form for that, constant tangential and linear normality. So this kind of basis function is called constant tangential and linear normality. So it is basically very useful for us later on. I will discuss that later on. So let's say if I want to write the field in this rectangular element, then I write E1, N1, E2, N2, E3, N3 plus E4, N4. E1 is the tangential component of the field along the S1 of the element E. and N1 is the interpolation function. Just like the E2 is the tensile component of the field along the S2, and N2 is the interpolation operation. Similarly, E3 is the tensile component of the field along the S3. On the electric field. Let's say I want to find the electric field in this. Let's say I want to find the fields inside this rectangular element, and what is the boundary condition on the electric field? Electric field is tangentially continuous, so that boundary condition for the electric field will be automatically satisfied by this kind of vector basis function. So that's why we are actually going for CTLN for the finding the fields. It actually permits enforcing the tangential continuity of the electric field, and it is actually called one form without affecting the normal components. In the two form, if you want to find the magnetic field, we actually call this as two form. In the two form, it is constant normally and linear tangentially. What is the boundary condition of the magnetic field? Normal component of the magnetic field is continuous. What is the boundary condition on the electric field? Tangential component of the electric field is continuous. So we actually go for constant tangential and linear normally for the one form. For the two form, we actually go for constant normally and linear tangentially. Whatever we have considered is for the one form, and this is what we are going to discuss in this class. So basically, this actually satisfies the boundary condition for electric field and magnetic field. That's why we are going for such kind of basis function. And one very popular basis function is called the Whitney element. So Whitney element is one of the vector elements on the triangle. We have considered for rectangle, we can actually consider what kind of basis function, vector basis function is there for a triangular element. And triangular element is very popular because it can fit into any kind of shapes. So let us try to find out what is Whitney element on the vector elements on a triangle. So this is what actually used in the isobasis, this kind of element. So we'll discuss that. So let us try to simplify, consider a right angle triangle of unit length along the x-axis and y-axis. This is what we're considering. We are considering a right angle triangle with unit length along the x-axis and y-axis. This is right angle triangle. So from there we'll derive it. But then this right angle triangle condition is not required. So if you want to look at this derivation for any arbitrary angle triangle, then you can always go to D.B. Davidson's book, and this is one of the book I have suggested for you. And D.B. Davidson's book, they have actually put in the appendix how to derive this Whitney function for any arbitrary triangle. So we will do it for right angle triangle because it's easier, but this holds true for any kind of triangle. So that's what I'm giving at the beginning. So whatever derivations we are doing is for right angle triangle, but it also works for any arbitrary triangle also. If you are interested, you can look at D.B. Davidson's book. In the appendix, they have the right angle triangle. The derivation is easier for us. And find out what is the Whitney function. So basically, right angle triangle we are actually considering. So we have defined three nodes, node 1, 2, and 3. We have defined edges 1, edges 2, and edges 3. This point here is P, and it is located at x, y. So let us try to analyze that. Okay, so we define some coordinates called simplex coordinate. In the simplex coordinate, lambda 1, in this lambda 1 is defined as area of triangle P23, area of triangle P23. This triangle here, P23. What is the area of this triangle? P23, half base into height, right? Half base into height. What is the base? This was of length 1. No? Base is 1. Height is how much? Height is the y. No? So P was x, y, so this height would be y. So area of this angle triangle P23 would be half. So lambda 1's simplex coordinates, lambda 1 is defined simply as y. because half y divided by half is y. Okay, so then we also define lambda 3. Lambda 3 is basically this triangle, area of this triangle, P12. P12 divided by area of the triangle 1, 2, 3. P12. P12. What is this height? Height is x. And what is this length? This length is 1. So half base into height, base is 1. Height is simply x here. Because P location was x comma y. And what is the area of triangle 1, 2, 3? Half. So lambda 3 becomes x. So we define simplex coordinate lambda 1 and lambda 3. If I want to find lambda 2, I use the property summation of the simplex coordinates lambda 1, lambda 2, lambda 3 equal to 1. If you take the gradient of that, you will get y hat. What was lambda 3? Lambda 3 was x. So gradient of lambda 3 would be x hat. What is the gradient of lambda 2? Lambda 2 was 1 minus x. So it will be simply minus x hat minus y hat. I have delta lambda 1, delta lambda 2, and delta lambda 3. From there, I can find out Whitney elements function for first order. You can actually go for higher order terms here. So we'll consider the simplest one, which is the first order term. And the first order term element function is basically defined as Wij. It's a vector. Wij is defined as lambda I gradient of lambda j minus lambda j gradient of lambda I. That's how you define this Whitney elements function. So you can find it out. You know what is lambda I, you know what is gradient of lambda j, so you can plug it in. For example, if I want to find W1, N1, just note that this is Wij, so then lambda I, lambda j, lambda j, lambda I. So if I want to find N1, then I find out W23 of the remaining two nodes, 2 and 3. So N1 is W23. W23 then what is gradient of lambda 2? Gradient of lambda 2 is minus x hat minus y hat. So finally N1 turns out to be 1 minus y x hat plus x y hat. You can also find out similarly N2 is W31. So N2 means then remaining nodes 3 and 1, W31. So W31 then lambda 3, gradient of lambda 1 minus lambda 1, gradient of lambda 3. It turns out to be x y hat minus y x hat. What is N3? N3 is remaining nodes are 1, 2, so W12, lambda 1.
Sir, voice not coming.
There are net issues. Okay, so let us try to make an interpretation of N1. N1 is W23, which is equal to 1 minus y x hat plus x y hat. So let us look at the interpretation of this Ny along the edges tree. Along the edges tree, so this is S3. Along the S3, what is happening? So along S3, y-axis x is equal to 0. If x is 0, this term is going to be 0. So the function is purely normal. So this term is 0 because x is 0. So we just have this term. So that means N1 is 1 minus y x hat. So what is the direction? Direction is along the x-axis and s is along the y-axis. So it will be directed like this, along this direction. So it is purely normal. Secondly, it increases linearly from node 1 to node 2. So from node 1 to node 2, it is increasing linearly along the S3. So 1 minus y means what? If you have a higher value of y, then it is small. So y is 1, then it becomes 0. So this is what is happening. So it is purely normal along these edges. So N1 is normal to the S3. So N1 is normal to the S3 and it is increasing linearly. This is what is happening. So this is how this vector look like, N1. N1 is increasing linearly along the S3 and it is normal to the S3. This is the hypotenuse of the right angle triangle. The function is purely normal. So along the S3 also it is purely normal. Look at this is normal on the S3 and it also increases linearly from node 1 to node 1 to node 3. Node 1 to node 3 it is linearly increasing. You can just plug in the values of x and y and find out, and it is normal to the S2 also, and it is linearly increasing like this. This is what is happening for N1. Let us look at the N1 along the S1. S1 y is 0, it has both tangential. So if y is 0, this is 0 here. So it has both tangential. So y is 0, then this term is constant. No? So this tangential component is constant and equal to 1. So this tangential component at y is equal to 0, this tangential constant is constant. Look at this tangential component because we are looking along the x-axis. So it is tangential along the S. S is along the S1 is along the x-axis. So this portion is going to be tangential along the x-axis and it is having constant value of 1. And it is also normal to the y-axis. It is linearly increasing with x component. This is normal, no? X, y hat is normal to the S along the x-axis. So let's look at it. That means along the S1, it is slowly increasing like this. Is it okay? So let us just divide this into two parts. First part is always come. And one more thing is that when you take divergence of the Whitney function, it is 0. So you can plot all this thing together. So what we are observing is that this S tangential x component is constant, but the normal y component keeps on increasing linearly. That's what we have observed just now. This is what we have. Tangential component is constant, but the normal components keep on increasing. So it is what we are getting like. So let us summarize. N1 W23 is a basis function with constant tangential component and linearly increasing normal component. Now we understand what I mean by constant tangential and linearly increasing normal component. So when y is equal to 0, this term is constant, but this term is linear. Discuss for the rectangular element. So let's say if I want to find out the fill for this kind of triangular element, then I can find it out with it as E1, N1, E2, N2, E3, N3. Where E1 is the tensile component fill along the S1 of the element E, and N1 is the interpolation function. Similarly, E2 is the tensile component fill along the S2, and N2 is the interpolation function. E3 is the tensile component fill along the S3, and the N3 is the interpolation function. This kind of element has been used in the high frequency structure simulator. This is what I usually cover during my previous courses. Okay, let me just stop the recording.